right, so what I kind of want to show people is that there's a pattern here to the periodic table. It's not just this random assemblage. There's actually some order to it. And let's see. So, and what you'll find is that all of the columns have some things in common.
Wow.
You mean in common?
In common, thank you. Yeah.
That's okay, we got it.
In there.
Yeah, like, I mean, okay, so you got hydrogen here, which is number 1, and of course that's got
Oh,
the
that's the
one
wrong way.
electron there, right? That makes sense. And then the next one over is helium, and notice how, can I put any more in this?
No.
Right, helium's number 2, and I can't fit any more in this first level, I have to go to the next level. And so then, with lithium, I'm not gonna write in the element names anymore. Oh, that's terrible.
That's a good circle.
Nice circle. We'll edit this out. Let's see. So
This
where
is the
was
best
I?
stuff right here.
There's 2.
Lithium, you were at
They were
Quality chef material.
Yeah. Here we are at lithium here, right? Lithium has the same 2 that hydrogen and helium had, but now we go to another level, and lithium has 3, and then we move over to beryllium. We add another one.
My neck hurts.
I'm not going to go through the whole table this way, just this row, just so that you know it's not total torture, just kind of torture. And then boron, add another one, carbon, add another one. Now we got 4 in the outside. Then with nitrogen, we would add 5. Oxygen, we'd have 6. This is fluorine, by the way. Let's see. Oh, look at that.
Awesome.
How nice.
Good.
Wow.
I was going to actually write exactly that on the back there. And so here's fluorine, and fluorine's almost full. What you can't see very well is that this is neon with 10, right? Just like in neon lights. And so then it would be full. Oh, and I did lie. I'm actually going to go over to the next row again. Just to show you one other thing. Look what happens. I start a new level here for now sodium, Na, number 11. And look, I have 1 in the outer level. And then with magnesium I have 2. Do you see a pattern here? Maybe?
A little bit.
A little bit. So every time you start a new row, remember, when we started, when it went from hydrogen to helium, and then we started a new row, we had 1 on the outside. This is true. And of course, with hydrogen, you had just 1 on the outside because there was just 1. And then we went all the way across, we filled it up to neon, right? Neon. And then when we went to sodium, we had 1 on the outside again. All these ones here have 1 on the outside. Turns out that that's how the periodic table is organized, is by the outermost electrons, for the, at least for these purposes. Everything in this row not only has the same number of outer electrons, with 1, but it also has very similar properties. These are all really active, chemically reactive elements, and you'll see why in a little bit.
It's like that for every row.
It's like that for every row. So these all have 2.
2.
And then moving over here, we ignore these. This is the, what is it? Like
Sea of the Dead.
in the Lion King, you know, that is the dark place. Don't ever go there. Don't. These are the transition metals. You'll learn about those in chemistry. They're dark and different, and they're
Can you undo
stupid.
this?
They're stupid.
No. Can you, like,
But anyway, so
unwrap
boron. Now we got
it?
3.
Never mind.
Remember 4, 5, 6, 7, and full. And it turns out, yeah, everything here
Eat it.
is full. Everything here is 1 away from being full. So forth and so on. And so like these all have 6, these all have 5, these all have 4. And that's the way the periodic table is organized, by the outer shells. And what I have to tell you, okay, wait, now we have questions. Yes, okay.
Why is there like the big separation from lithium and beryllium from all the other?
Because, well, it's in the same way with these. It's because these, remember we talked a little bit yesterday about how when you get into some of these larger ones, the electrons go in weird pockets, like they go in weird orbitals that aren't normal. So these are the normal, like, outside orbitals that are like normal and not weird and strange and dark. And then once you go here, these are the ones that have 10 electrons that go in an orbital underneath that act strangely. And so we don't talk about them in relation to this. So we're talking, when we talk about outer electrons, we're talking about outer electrons facing the world. And it turns out that that's the important thing. When you look at,
Oh,
I know.
That was tough.
that was a little crazy.
When you look at elements, Like, it doesn't matter, like, what is inside, it's what's outside. So this is the opposite of what you've been told all of your life. It doesn't matter what's on the outside with your clothes and all. It matters what's on the inside. Not in chemistry. It matters what's on the outside in chemistry. Chemistry is very superficial. It only cares about the outer electrons. And so, because those are the ones that interact with the world. So whether it's hydrogen with one electron on the outside, or lithium with one on the outside and a couple on the inside, or sodium with one on the outside and 10 on the inside, or any of these, even francium, same way, one on the outside and like 86 on the inside. It doesn't matter. They all act the same way because what matters is this one. And that is why they do what they do. And in order to talk about that, I want to talk about these. Right? What are these? These are
Gases.
gases. Do we remember what? Does anybody from like 8th grade or whatever know what's true about these gases?
Well, they're like they don't react to anything else, right?
They don't react with anything else. That's right. These are the
Noble gas.
noble gases. Because
Nice, dude.
and they're also called inert.
Yeah.
Do that again.
Inert,
Yeah.
inert. So what is it about the noble gases? They don't react with anything. They don't form any chemical compounds. They and what are they all? What are they all?
Gases.
No, they're all full.
They're all noble.
Oh yeah, yeah.
They're
That's why they
all
can't react. 'Cause they're full.
They all
They're full of
have
themselves.
like here's neon. Neon is number 10.
There it
It's
is.
full. And it turns out that when you start a new row and you go all the way across, 1 on the outside, 2 on the outside, 3, that's aluminum by the way, 3, silicon 4, just like carbon. Phosphorus has 5 on the outside, just like nitrogen. Sulfur has 6, like oxygen. Chlorine has 7, just like fluorine. And argon is full, just like all the rest of them. And it turns out that that's true of all of these, and that has an effect. The only elements that don't form bonds with other elements are these, and it's because they're full, because they have this full outer shell. Even helium, which if we go back and think about helium, helium. If we go back and think about helium, only had 2, but 2 was enough to fill it. Remember, you had to, once you got to helium, you had to move to another level because helium's full also. Turns out that makes them happy. And being the next ones with just where you have to have 1 on the outside, they're not happy. They're not stable. They're not stable. Think of it like a shoe in the dryer or something like that. Like,
Oof.
as they go around. It's just not, they're not happy, they're not balanced. Once they're full, they're stable. If you give them 1 less or 1 more or even any of these other things, they're not as stable as they are. So literally, when you go from like chlorine or fluorine's configuration to that of neon, the atoms like, they like stabilize. It's like this thing. They're all of a sudden like they change size, they get really compact, and they don't all of a sudden have any reactions with anything else. Everything else on the periodic table except for them undergoes chemical reactions, and that is so they can be like helium, neon, argon, krypton, xenon, and radon, which is number 86 there, and somehow its card is missing.